sector. She pursued her master's degree at Yale University, US, where she also completed her PhD in the year 2009. Sorry. Her dissertation focused on statistical modeling of brain activation patterns for robust analysis of functional MRI. Before joining IIT Ropar, Dr. Bathula held a research position at Oregon Health and Science University, where she contributed to biomedical imaging projects. Her current research is centered on the development of computational and statistical techniques for medical image analysis. She specializes in image and signal processing, pattern recognition, machine learning, deep learning, with the goal of enhancing diagnostic decision making in healthcare. Dr. Deepti has published several journal and conference papers of international repute. She has also received numerous research grants and consultancy projects from several funding agencies like DST, SERB, DVT, and so on. So through interdisciplinary collaboration, she continues to advance solutions at the intersection of computing and medicine. With this now, I request Professor Deepti to kindly start the session, and over to you, ma'am.
Thank you. Thank you so much for the kind introduction. I'll just share my screen if you can tell me. It's visible?
Not yet, ma'am. Yeah. Yeah, it's visible. Yeah, it's visible, ma'am. Yes, ma'am. Please start.
Okay, great. First of all, thank you so much for inviting me to this FTP and giving me an opportunity to speak to you all. The overview of my talk is structured in this way. So I think considering the actual topic of the FTP, most of the members would have already heard quite a bit about, deep learning and its importance. So we're not going to spend a lot of time on this, just a little bit of an overview on the importance, the advantages, and the current challenges that the domain actually faces. And following that, I would like to share a few of the pieces of work that some of my lab members have been working on towards addressing some of these challenges. So hopefully it'll be of interest to most of you. So before we go on, I just want to motivate why we should be, thinking or considering artificial intelligence for medical imaging, right? So again, some of the numbers that you see on these slides are quite old, to be honest, and they're actually from US. But if you see on the in 2011, the United States had actually recorded about 80 million X-rays, 30 million MRIs, 69 million ultrasounds, and so on. So the numbers are really, really large, right? Although we might not be able to extrapolate them to Indian demographics directly, but considering that we are very far into the future. I mean, these numbers were from 2011 and we are already, in 2025. And, and also, the medical facilities, the hospitals have increased quite a bit in India. So I would think the numbers would be of the same order, not very significantly different. So one is this challenge, right? There are a huge number of images being generated on a daily basis. And so being able to analyze them, manually is a very tedious and a very time-consuming task that requires, a lot of, medical expertise. And we can imagine how, overloaded our doctors will be to be able to do that manually, right? And at the same time, the other side of the coin that I would like to kind of highlight is that the heterogeneity that is very, prominent to the medical domain. So you can imagine that some of these images on the left-hand side, they show you some variety of images. Again, they're not very comprehensive. There are very few samples. You have your MRIs, you have your X-rays, your mammograms, your, digital retinopathy images, you have your dermatological images. So there is a huge variety of these images being, generated on a daily basis. And the tasks that we would like to accomplish on each of these is very different. In some of these images, we would like to, do classification. Some of them we would like to be able to delineate the organs of interest. Some of them, so the task that we would like to be able to achieve is also very varied. So this is what, from my perspective at least, is what motivates why we should be looking to AI as a solution to the medical imaging domain. The next thing, again, coming from a academic perspective, I think this is of interest to most of us. These are, again, numbers relatively old, but you can see the number of publications that have been, in the direction of AI for medical imaging over, in 2017 that have been recorded. The split has been shown according to different imaging modalities. So you can see MRI, CT, ultrasound, and so on, and the number of publications. And again, as I said, these numbers are relatively low considering this is about 8 years ago, right? Again, we have the split up based on the, the pathologies or the regions of interest. We have the tasks themselves, classification, segmentation, and so on. So the increase in the number of these research, publications is significantly large, and it's increasing even more as we go forward. So both from a practical clinical application as well as from a research perspective, AI is of a significant importance to our medical imaging domain. And the other aspect of it is that if you think about the medical imaging domain, there are a significant number of steps that we go through, right? So for example, we start with actual acquisition of the images, from using the hardware that we work with. Then in some of the modalities, like for example, MRI, the data that we acquire is not very standard. It's not in the imaging domain. So we have to do the reconstruction process. Then we probably have to do some, pre-processing. We have to do the visualization, then being able to go on to do this pathology detection and a whole lot of other steps. So one thing that is very interesting or very prominent is that AI has literally affected every single step of this workflow. It's not that it is only being used at the end of the cycle where we can only use it for diagnosing or treatment prognosis and so on, but it is actually being used in every single step. For example, MRI image reconstruction, where we do it from a Fourier case space to a normal imaging space. People have been using AI to kind of supplement the, or reduce the amount of time in the MRI scanner, but trying to reduce the number of samples in the case space, right? And they've been using AI algorithms to supplement that information. Similarly for, visualization and so on and so forth. So the whole pipeline, the whole workflow has been, significantly affected for the better using AI in this particular domain. Now, it's not to say that we have not been doing this. Since ever, I think prominently from early 2000 itself, we have been actually using computers to help this process, make it easier and a bit more, user-friendly for us. But the traditional approach actually involved a lot of user inputs, in the sense that depending on the particular modality, depending on the particular organ, the pre-processing steps had to be, specifically designed. The features extraction steps had to be, done very specifically for that particular thing. And it needed a lot of domain knowledge. For example, it couldn't have been accomplished without, collaborating with doctors and getting their inputs significantly to be able to do this very efficiently. Of course, there are a lot of generic features, but still being able to do it efficiently needed a lot of domain knowledge. And every single task or for every single modality and every single organ, we had to develop, different algorithms to be able to accomplish this particular task. And so what deep learning actually has been able to provide, or it kind of promises, is that we don't have to do so much manual intervention. So if you look at this particular picture here, the top part of the picture tells us, the actual traditional approach where we do the pre-processing, we do the feature extraction manually, then apply, some machine learning algorithms or other task-related algorithms to be able to accomplish the whole goal. However, the deep learning algorithm, as highlighted on the bottom, the blue square, basically says that, you don't have to do so much work. Let me do the work for you. I'm going to have this complicated network that's going to take my images as input. It's going to do some of the processing. It's going to do some of the feature extraction automatically. And it's going to try to give us the features that we can, towards the end, put it through some classification or regression tasks, and we'll be able to get those results quite automatically. So basically the promise or the potential is that we don't have to do a lot of work, but the deep learning algorithm does it for us, by significantly reducing the user input. So that's the major claim that the deep learning algorithms actually give us. But having said that, and it's not it's not a very big surprise, the deep learning algorithms have been doing very well, not just in the medical domain, but even in the normal computer vision related domains. They've been doing a very good job. And some of the results that have been published are, really high end. towards, and in some cases even beating the doctors, as they claim. But it has been doing a really good job of it. However, when we talk about applying AI or deep learning algorithms to the medical imaging domain, we have to keep certain aspects in mind. So even though the generic algorithms that are doing very well, they cannot be taken as is and applied to the medical imaging domain very directly. There is a bit of an issue, and some of these challenges that the medical imaging domain faces is some of them that I've listed here. Is one of them is the limited annotated data sets, in the sense that when we talk about normal computer vision related tasks, so imagine doing classification or segmentation of some objects from images, right? So from day-to-day images, whether you want to segment a face, whether you want to identify apples, oranges, dogs and cats and things like that, the number of images that we have available is huge. Just Google it and you get lots and lots of images. And even the annotation part of it can actually be crowdsourced. We can just, have a whole bunch of people come in and annotate the data set for us. And so we have these large cohorts of data that we can actually work with. And that's what actually lends majority of these results, their accuracy, right? Because the algorithms have been trained on large data sets. However, when we come to the medical imaging domain, it's a bit different, right? As it is, we getting access to large data sets, although it's feasible, it's getting better now. It's still very limited compared to, lakhs and lakhs of images that we have for the computer vision domain. Majority of the medical images, data sets are about, on order of thousands or something. And then even the annotation. And why is it limited is because the experts need a lot of time to spend on the data set to annotate it. Well, if you imagine, segmenting an organ, we cannot crowdsource it, and a person who's trained and is familiar with the particular domain can do the best job, and that is what we rely on. So the expert's time is significantly expensive in this case. High dimensionality is again another issue. Most of the images that we deal with on a day-to-day basis, the new normal images on a day-to-day basis, they're very low dimensional, maybe 512 by 512, and we have this RGB components. But majority of the medical images are really high dimensional. For example, MRI images 3-dimensional, and roughly goes of the order by like 100 by 100 by at least 50 slices. So you can imagine the size of the images is very large. On the contrary, by taking into account the limited annotated data sets, we have a very opposite problem. We have high dimensionality and low sample space compared to the normal computer vision domains. Class imbalance is again a very crucial issue, because when we're trying to do tasks like simple classification and so on, the positive class pathological class samples is generally very limited. For example, let's imagine we're doing looking at medical images for major depressive disorder. So when we conduct a study, something like that, it's easy for us to get a lot of normal people to participate in our study. But getting depressed people to participate and get their data collected is significantly difficult. And so most of the medical imaging data sets that we have access to, we see a huge imbalance. For example, maybe 80% normal and 20%, actual positive cases, or in some cases even less, 90 and 10. So being able to design algorithms that deal with such class imbalance is going to be very important. Heterogeneity, again, a significant issue, because when we come to the medical imaging domain, there are a lot of differences, variations that actually happen, just from the fact that different machines can produce slightly different characteristics of the images. For example, a 1.5 Tesla MRI scanner versus a 3 Tesla MRI scanner will yield us different images, different quality images. Maybe even the heterogeneity in terms of the demographics. For example, the images or of the people that we have taken in the US might not necessarily translate to the Indian demographics. So there is a huge heterogeneity in terms of the machines, the acquisition protocols, the demographics, and so on and so forth. And as a result of this heterogeneity, the generalizability becomes a problem. Why? Because, for example, let's imagine we trained an algorithm on publicly available data sets that majorly come from US or some other European countries. And if we try to take the well-trained algorithm and try to test it on, let's say, a small data set that we collect in India, maybe it will not be very, easily generalizable. It will not translate as easily because of this heterogeneity related problems. The last two again are some of the things that go, kind of hand in hand together because of this, complex nature of the deep learning algorithms, the inherent non-linearity that happens, the interpretability, and the issues actually happen, and so we're not able to understand why a neural network or a deep learning algorithm is giving us the solution that it is actually telling us. Right? Why is it classifying some image as a positive case or a negative case? And so because of this lack of transparency and interpretability, we also have this privacy and legal issues. Like, for example, in Europe right now, AI algorithms are kind of banned for safety critical applications like the medical domain, the law, and so on and so forth. So they're not easily applicable. Having mentioned these challenges, I would also like to highlight that there is a lot of effort currently in the domain to address these challenges. So, for example, the limited annotated data sets, people are now more and more forthcoming in terms of publishing the data sets. So we have a lot of benchmark data sets compared to back in the day when I was doing my PhD. So we had very limited data then, but now it's a lot better. We also have, algorithmic improvements. For example, we have data augmentation algorithms. So we can actually take our limited data sets and we can, apply some algorithms to generate some synthetic images that can help in the learning process. The high dimensionality of the images, we can deal with them using things like simple, like patch-based models. Instead of saying that I'm going to read the whole image and try to train an algorithm and that complete image, let me do it on patch-based things, and then I'll try to accumulate the results from the final, composition of all the patches. Similarly, class imbalance is again, as I mentioned, is an important thing. So simple techniques like random sampling, upsampling, or downsampling techniques have been used, and recently generative adversarial networks have been used to generate samples of these rare classes, or classes for which we don't have a lot of samples. So that's again been very, very useful. Heterogeneity and generalizability. People have come up with domain adaptation and transfer learning related algorithms that actually say that, by looking at or training an algorithm on one domain, just by using a little bit of data from the other domain, we'll be able to kind of, help the algorithm perform better on the target data set. So these kinds of algorithms have been available for a while now. And the other, the transparency, interpretability, explainable AI. I don't think I have to, mention a lot about it. It's a very upcoming, kind of an area. Quite a few people are putting in a lot of effort in the XAI kind of direction to try and come up with algorithms on which we just don't get the final answer, but we're also able to some extent at least, understand the reasoning behind that answer, the predictions, right? So that is actually being done. Again, federated learning has been one of the options for reducing privacy related issues where we don't have to share the real data itself. So these are some of the efforts that have been used to address these issues over the recent years. So I would like to take this opportunity to share a few pieces of work that we have been doing in our lab towards addressing some of these issues. So one of the things I just mentioned is the small sample size and also the class imbalance, right? So we would like to be, one of the things that we addressed was this particular issue. And are there any questions? I'm not able to see any responses. Please do feel free to interrupt me if you have any, right? So in this, for this particular case, we have actually worked with a meta learning kind of framework where the idea is that we want to, not train a network from scratch. The idea is if we train a network on a similar kind of a paradigm, adapting is, relatively simpler. Okay, so this goes by the analogy that I always use to explain meta learning is that we humans are quite efficient. We don't take as much effort to learn newer things as the machine learning models. And the reason behind it is we use our previous experience, the prior experience, to apply to newer tasks, right? So the example is that if we actually already know how to ride a bicycle, riding a motorbike becomes relatively simpler task, right? So we spend a lot of time learning the bicycle, but after having learned that, riding a motorbike becomes very easy, right? So that's the kind of example or the framework that the meta learning actually uses. It says that it's going to use prior tasks to prime a network such that it is in a good position to learn a new task, kind of generalize to a newer task. There are several different paradigms within the meta learning framework. In that, we actually focused on something called the few shot learning. And so the idea is that when you have some classes with a lot of samples, but then you don't have so many samples for some of your classes, right? There are very few classes, the rare classes, the rare diseases, and so on and so forth. So expecting to train a large network that has seen lot of samples, and then kind of expecting it to work on some other classes that have very few samples is a kind of an unreasonable request, right? So the few shot learning basically says that by trying to match the training and testing conditions, you're able to prime a network to be able to do the task better on the novel cases. So, for example, in this case, what it means is that if we have a lot of examples of cats and birds or flowers and bikes, even though we have a large sample, we don't use all of them at the same time to train the network. Every single time we train it as an episode, as it's called in few shot learning, we only give very few samples. So for example, I give 4 or 5 samples of cats and 5 samples of birds, and let my algorithm learn a set of features such that if I give another unseen example of a cat or a bird, it is able to classify it very accurately. So this is the idea. So we basically say that we keep on training our network. It's not just once or twice, but over a lot of episodes, we keep giving our network very few samples of a particular class and test it on the unseen samples of the same class, just to make sure that it is learning to distinguish using very few samples. Having primed the network in such a way, if you now give it different kinds of classes that have not been seen before, for example the dogs versus otters, it will it is expected to do better because it has been learned to learn to distinguish using very few samples at a time. So that's the idea. So within meta learning, we actually explored the idea of this few shot learning. And within few shot learning, prototypical networks is a very famous framework that basically says that by learning the representation of the samples, by teaching our network to find a representation such that when you cluster those the representations of the support samples that the network provides, and by using the simple distance metric, whether it's Euclidean distance or whether it's a cosine distance metric, we check for a query sample how far it is from the prototype of each of the class, and depending on the closest distance, we basically classify that as the class of the query class that we actually do. So it's a very simple setup. So it's a very simple and very efficient way of doing this few shot learning. And so what we wanted to do was we actually took this and said that all the prototypical networks is very efficient and quite good. It kind of lacks one simple idea, that it was always weighing all the support samples equally. So if you see the 5 samples in each of these cases, the green samples, all of them are actually given the same weight. But we know that, in general, what happens is some of the samples are very representative of a class and some of the classes actually almost look like outliers, right? So we wanted to explore this particular idea where we said that, we should be giving some importance to the samples, and based on that, we should be creating the prototype. It's not that all the samples are equally weighted. And so based on this, we had actually used this. So this is basically the framework for the prototypical networks, where the prototype of each class is created by taking the representation of all the support samples and taking the average of that. So that's actually shown in equation 1. And when we are when we given a new sample, the way we try to figure out its class label is by looking at how far each of the prototypes of the classes are from the given sample, and based on that distance, we assign the label. And so we basically took the exact same framework and extended it to use the idea that some of the samples are more influential than the other ones. That's the simple idea. And so for this, we actually had used this maximum mean discrepancy. And so the idea was that we would look at the distributional difference between the samples, all of them together, and when we remove a sample. If the distribution changes significantly, right, then we know that the sample is kind of an outlier. But even if we remove one of the samples from that distribution, the distribution happens to be relatively very similar. We know that the sample actually matches the characteristics of that particular class. So using this MMD metric, we were able to give each of the samples in the support sample set a weighing factor, and we basically call it as the influential weight. And so the simple update was that the equation 2 from here, which was actually looking at simple distances between the prototype and the other samples, we had updated it to make sure that the influence of each sample was taken into account, so that we weight each of those samples accordingly. And so by doing this, we had experimented this using 3 different dermatological data sets. And as you can see from the characteristics of the distribution, there are quite a few samples for some classes, which are shown in red here. And for some of the classes that we call it as rare classes, or, kind of not so common classes, we have very few samples, the blue classes. And so this is one of the characteristics of the class imbalanced long tail distribution classes. And the way the experiments were set up is that we train on the classes that have large number of samples, the red samples, the red classes, over a lot of episodes. And then we try to test it on the blue classes where we don't have a lot of samples. And so we had done some experiments, and using 3 different data sets that I just mentioned, the dermatological data set, I6 2018, Term 7 PT, and SD 198. We were able to compare it with the prototypical network, the traditional one. And there were some variations of prototypical network, which were called as MDD-net, and also RRP-net, which was, again, kind of a reweighing strategy. And IP-net was our contribution to this. And as you could see, for different kinds of tasks across 3 different data sets, IP-net was able to show some significant improvement in the classification accuracy. The few shot learning is generally characterized as N-way K-shot. So N-way means we are trying to do N-way classification, and the K-shot is basically how many samples, support samples, we are feeding every single time. So as you can see, we had tried it for 2-way, 5-way classification with 3, 5-shot, different examples. And across the board, it was relatively doing a very good job of it. The same time, we had also tried some cross-domain experiments where we said that because all 3 of them are dermatological data sets, we should be able to train on one and test on the other. And so even in the cross-domain experiments where we had, let's say, for example, train on Derm 70 PT and then tested on SD 198 and ISIC 2018, we were again able to see that it generalized relatively good and was able to give us a decent improvement in the accuracy. We had attempted a little bit to see how the classes were segregated using the TSNE plot, and it was relatively good in some cases and not so much in some cases. But the left-hand side was a prototypical network where you could see the prototypes given as the triangles are relatively close to each other. The middle one was, I think, MDD-net, and the last one was IP-net. And as you can see, in some cases, the visualization shows that IP-net is better, but in some cases, even the MDD-net did relatively decent and similar to the IP-net. And this work of ours was actually published in ISB 2022. If there are no questions, I'll move on to the next one. I think it's in chat. How to distinguish between already learned and to be learned? Is there a mechanism? And sorry, I didn't quite understand that question. Between already learned and to be learned. You mean the classes that have already been checked?
Ma'am, actually participants cannot unmute their mic. They can only write in the chat box.
Okay, okay.
So I think that was the thing. I mean, I could also understand the same thing. I mean, the new classes, how the new classes will be learned like that, maybe.
So the best way to explain it is that the task that we're doing during the learning process is kind of similar, but not exactly the same. So instead of saying that, when I showed you this, the idea of these ones, right? So we were saying Let's imagine I have, 5 or 6 different large classes. I have cats, birds, flowers, bikes, and so on and so forth, right? So by changing the tasks randomly every single time, let's say in episode 1, I'm doing classes, cats versus birds. In episode 2, I'm doing flowers versus bikes. In episode 3, I'll do, let's say, birds versus bikes and cats versus flowers, and so on and so forth. We keep on randomly changing the task in each episode, and we keep on giving it very few samples of each class and then testing it on the query sample, right? So what happens is, instead of saying that, I want to learn exact difference between cats and birds or the exact difference between flowers and bikes, I'm priming my network to learn the differences between, just to distinguish between the two classes, any two classes. And because you're doing a lot of variation, it actually gets primed to say that whatever the few classes that I'm seeing, the 2 classes or the 3 classes, the distinguishing features have to be optimized. And so over time, those particular features will be, kind of given more importance, and it starts to extract those features that separate the classes as far as possible. So having been primed to do that, the last set, when we give the testing classes, which have not been seen, again, so the dogs and otters were never included in the training classes, right? So because this variation has been happening over a large, sometimes the episodes are like 2,000 episodes and so on. Because of a lot of variation in the classes and the support samples and so on, it gets primed to do the difference. And again, I'm not saying we don't show dogs and otters. We show very few samples. We'll give 4 samples of dogs, 4 samples of otters, and we now give another dog, and it will be able to classify much, much faster than saying that I only have very few dogs, very few otters. Let me train a network from scratch. So that is where the meta learning framework helps. I hope that addresses the question. Does it make sense? If the model is tested on dataset with 7 classes, how can resulting results be generalized for a data set with, say, 9 classes? I hope that made sense. The classes, I think maybe there's a bit of a confusion in terms of a data set with classes. It's not the data set with the X number of classes. For the few-shot learning framework, the classification task, as I just mentioned, we always configure it as a N-way K-shot paradigm. Whether you're dealing with 7-class dataset or a 9-class dataset, the classification is always performed in a N-way K-shot way. So once you fix it, let's say you fix it as a 3-way classification or a 5-way classification, that is what can be tested for your unseen classes as well in your data set. I hope that makes sense. It's not the data set related classes that is what is distinguishing, but it's the framework in which you establish the few-shot learning. It's the N-way K-shot. Once it's set, you have to set it. In fact, that's what you set it and train it over and over. You can only use your remaining classes or the unseen classes to be tested in that framework. I hope that makes sense. N-way is the number of classes that you want to distinguish at a time. So for example, even though we had, for example, let's say in SD 198, as you can see, we had a huge number of classes. We had, I think, 125 classes or even 200 classes altogether. But the actual classes that had a lot of data were about 125 classes. The classes that had very few samples were from 125 to 200. So the training process happened on these red classes, and we fixed saying that we will do 2-way classification with 3 examples at a time, or 5-way classification with 5 examples at a time. So once the algorithm has been trained, you can again give 5 classes or with 5 examples, or 2 classes with 5 examples from these blue classes, and that is what the network will be able to help you classify. For machine, bicycle, and bike example are entirely different. So how it applies already learned to learn in your class. So that's what I'm trying to explain. So in some sense, what we're just trying to say is the balancing is what we are learning, right? The same is similar for the bicycle and the bike. The difficult part is balancing a vehicle. So if you learned how to balance during the bicycle, the bike can also be done. Similarly, during this training of episodes over multiple classes, randomly changing classes with new samples every single time, the machine learning algorithm is being primed to learn the distinguishing features. It's not trying to learn explicitly cat versus dog or flower versus bike and so on and so forth. It's learning generally, how to distinguish between two classes. And so when you give new two examples, dogs versus otters, it is helpful in picking the distinguishing features that will help you learn, apply it much faster. Um, Is two-way classification the same? Yes, two-way classification is binary classification. Five-way is if your classes have 5 different labels, you want to do, in that way. So yes, you're right. Two-way classification is binary classification. I hope that helps explain the bike versus the machine learning paradigm. I know it's a very crude example, but that's the best I think I can give. Does that help?
Yes, ma'am. Yes, ma'am. Please.
Oh.
Thank you.
Is it possible to apply different objective in the first optimization step and the meta optimization step? I'm assuming you're talking about different objective. Like for the IC dataset, there's a huge class imbalance in classes. How reliable are the results without augmenting the actual dataset? Sorry, let me go back to the other step first. Is it possible to apply objectives in the first optimization step and the meta? I don't think we've tried that. The optimization, the objective has always been to do classification. So either if you're talking about doing classification versus another task, like let's say regression, I don't think that will work. Or if you're talking about, let's say, doing 3-way classification during your optimization and then let's say 5-way classification, again, I don't think it would work, because the network, the way you design it, that way you train it, is what is being used to test it. Changing the configuration in between, I don't think really, or at least I have not come across a similar kind of an approach before. For ISIC 2018 dataset, there is huge class imbalance. How reliable are the results without augmenting the actual dataset? Okay, so I guess I kind of missed that part. We did do some augmentation, but very simple augmentation, like rotations, mirror flips, and a little bit of scaling and so on and so forth. So yes, we do the augmentation, but only for the training classes. So we've actually been able to do that, and so then we extrapolated to the testing classes without actually doing augmentation. So yes, there is a huge class imbalance. In fact, that's what the whole idea of few-shot learning is, that without being able to see a lot of examples, your starting initialization point of the network is helping you achieve that level of classification accuracy. Like contrastive pre-training in first step and then classification. Could be. I'm not quite sure actually. I haven't seen the latest radio. At least I have not seen this before, but it could very well work. It just might be a little bit of a framework that needs to be adapted properly, is what I would think. So I think we've come across something like self pre-trained versions before and then later, but I would not comment on that without knowing the actual literature. How would few-shot learning compare to transfer learning in CNNs? In this case of class imbalance. So transfer learning, agree, very valid point. Transfer learning is definitely an alternative that could be considered for, instead of few-shot learning. But the idea is, for transfer learning to be very effective, the data sets have to be, or the tasks have to be relatively similar. What we have noticed is, even in terms of, for example, the transfer learning is very, used a lot in medical domain, because we don't have a lot of samples, or even in this class imbalance case. So what happens is we take these pre-trained networks from, other domains, like for example, ImageNet trained algorithm, or, somewhere. So what we notice is, if we do that kind of transfer learning, it's not very efficient. You don't see the same kind of performance. But if the task is similar, in fact, people have, I think there was some literature that compared pre-trained networks on computer vision datasets versus pre-trained networks that have been trained on medical domain datasets. So when you did the transfer learning from medical domain to this, it was relatively better than the computer vision to this one. So the quality or the improvement that you can achieve with transfer learning kind of depends on the similarity of the data sets and similarity of the tasks on which the pre-trained network actually has been trained on. So that's the main this thing. But I wouldn't definitely say as a blanket rule that across the board few shot learning will perform better than transfer learning. No, it's definitely a competitive alternative. But yes, it depends on the the kind of transfer. So because most of our example, as we have seen, we were actually able to focus on a particular domain. So the dermatological data sets, the ISIC data set, the term 7PT, and so the the learning was better in transferring that information across the episodes to the novel classes. So that's what it would be. Yes. Okay. I hope addressed most of the questions. So I'll go on to the next topic, and yeah, please, any questions? That'd be great to have. So the second topic that I had, we would like to share, at least given the time, is the idea that these, most of the deep learning models are really, really large, right? So when it comes to the medical domain, if you would like to be able to deploy them, it becomes a major issue. So imagine, we would like to be able to do point of care testing devices and so on and so forth. So one of my students had shown interest in looking at this model compression. So we want to be able to generate lightweight models that can be easily deployed, but at the same time, we don't want to affect our performance significantly. We would like to be still able to perform, relatively high. And so this basically comes under the topic of model compression. And it's not a very, unknown thing. It's quite popular that these neural networks have a lot of redundancy in them. In fact, some of the pruning algorithms that have been published in recent times have shown that after training the network, if you have some pruning strategies, when you apply them, even up to 50% of the nodes can be removed without actually affecting the performance of the network. So we know inherently there is a huge amount of the redundancy in the networks. And so we would like to, the goal was we wanted to be able to exploit that to come up with lightweight networks that can be easily deployed. And so the thing that we started looking into, so there are several alternatives for model compression. There is pruning strategies, there is quantization strategies. One of them is knowledge distillation. There is another low rank factorization. So our work focused on knowledge distillation. And the idea is very simple, that we start with a very large network, which is called as a teacher network. And after training that network, we know that the network has a lot of redundancy. So what we then do is we start training our student network, which is comparatively relatively smaller and lightweight network. And what we do is we take the knowledge that the teacher has learned and distill it to the student. So instead of saying that everything has to be flow, instead of all the different information that the teacher has gathered through the training process, we'll take the most important information and distill it to the student. So this was the idea behind knowledge distillation. And the idea that my student had come up with also uses another paradigm, which is basically called as this mutual learning. It's again very similar to the knowledge distillation, but knowledge distillation inherently assumes that the teacher network is very large and the student network is very small. Mutual learning can actually happen between two equal, networks. They can be very similar, but they share the prediction. So it's a kind of an ensemble kind of a technique where we say that instead of not just from the data and the labels, the networks also share this, information between them to enhance their learning strategies. So we have knowledge distillation and mutual learning. So my students' idea basically comes from the natural, classroom setting, right? So if we think about it, when a teacher is teaching, of course, the teacher helps the student understand, but we also see sometimes the discussions between the students actually help it make it much more clear. Maybe it's because of the language that they use, the way the ideas are shared between them. It's a kind of a similar strategy, right? So that they learn, easier between them. So the idea was a very simple extension. We just said that instead of having a single teacher and a single student, we have the single teacher, multi-student framework, where the teacher is teaching the students, sharing information with both the students, but at the same time, we also have the students sharing information between them. So this is a combination of knowledge distillation and mutual learning with a single teacher, two student network. We because of computational resources, we didn't extend it further than a single student, sorry, two students, but we tried it with different combinations of these. So the idea is relatively very simple. So the teacher itself is trained using normal data set with the ground truth labels using the cross entropy laws, but the student actually has multiple components. Of course, the student is also given some images and their corresponding ground truth labels. So there is the cross entropy component of the loss. Then the teacher is sharing information. So there is this knowledge distillation term in the loss function where we are saying that any discrepancy in the teacher's predictions and the student's predictions is penalized, right? We want our student to perform as closely as a teacher. And the last term is saying that in addition to the ground truth labels and the teacher, related information, I'm also sharing knowledge between the students. So again, any discrepancy between the students' shared labels is also kind of, optimized together. So all three terms are optimized in a joint fashion. So as I said, the idea itself is relatively simple, but the main issue was that now instead of talking about simple one student network, we're talking about two students. So we should still be able to show that this is a very efficient setup, right? If the compression is not happening, enough, then the idea of having two students is a much more expensive proposition. So we tested this particular thing on 3 different teacher-student network configurations. So as you can see, V1, V2, V3, we had ResNets of different VGG, DenseNet, EfficientNet, and so on and so forth. And the graph below shows, the compression between the teacher and the two students combined. We are not talking about one student, but both the students combined. So we can get about, across these 3 configurations, we were able to get about from 30 to about 47% compression in the model parameters. So that's relatively significant, we would think. And we had tested this on 2 different tasks. One was the classification task of this histological images, and the other one was the polyp detection in the GI tract images. So 2 different tasks we had actually tested this on. And as you can see, for both the classification and the polyp detection tasks, the ensemble of the 2 students. Why? Because we are now training the 2 students independently from the knowledge of the teacher as well as the students themselves. And so the final predictions that we had taken was the ensemble of them. And that's why the network parameters were also calculated as joint student 1 plus student 2. And so when we actually looked at these results, we were actually able to see that the knowledge distillation plus the mutual learning actually had, shown significant improvement in both the classification as well as the polyp detection, performance. So relatively decent performance was observed with decent amount of model configuration. So this work actually has a next piece I forgot to incorporate. We had extended the strategy again to say that, again, taking the whole classroom paradigm even further, we had assumed, or we wanted to incorporate that, different students have different ways of learning. Even if you notice in a normal classroom, right? Some students like to listen to the teacher, some students like to do the experiments to learn, some students like it visual, when they're shown pictures or videos and so on. So every, student has their own way of learning. And so we had extended this thing to actually say that even though we have this teacher-student network, the teacher doesn't share the same information with all the students. The teacher shares maybe predictions with one of the students, the teacher shares features with the other students, incorporating this heterogeneity of learning between the students. And that particular thing actually had given even further improvement in the actual model compression results that we see here. So hopefully we can actually take a look at that. Okay. Before moving on, I do have one mention with the direction I was exploiting. This short mention by the direction of the data. Thanks for the discussion. Okay. So that's about the model compression component. If anybody has any questions, we can take them at this stage. Sorry, Dr. Deepak, I'm not sure about the timing. It's about 7:20. What is the situation? I mean, is it?
You can continue, ma'am. You can continue, ma'am. No problem.
Okay. Sure. So maybe just one last topic. Hopefully, something of interest to most of them. Actually, I'll just go to some of our latest work here. This is the calibration. So again, in the medical domain, this is an important thing. Just so that we can actually have a small discussion on this. So in safety critical applications in medical domain, it's not just the classification accuracy that we would like to be able to focus on, right? We also want to have a decent confidence in the results that the algorithm is actually presenting, and so calibration is one of the metrics that actually looks into this. And so this was what we had recently looked into as part of our work as well. So how do we define calibration? So I guess even in literature, there are a couple of different, definitions, but the most popular one actually describes calibration as the disparity between the true confidence or the accuracy and the predicted confidence or the output probability of a particular model. So if you imagine that the main way people generally look at calibration is the plots that you can see at the bottom. Here we can actually see accuracy versus confidence, right? And the blue bar graphs that we can actually see. So the way these are plotted is, for all the test samples that your algorithm has been put through, you look at the output probabilities of each of those samples and you bin them. Let's say you bin them into 0 to 1, 0.1, 0.2, 0.3, and so on and so forth. And within each of those bins, that have been done according to output probability, you also look at the accuracy of the samples in that particular bin. So when you plot this, if it's a well-calibrated model, you actually get a very nice, identity kind of a line with the diagonal this thing. But if there is a discrepancy in the output probabilities, predicted probabilities, as well as the confidence in those bins, you see a significant gap that you actually see in the right-hand side. So as you can imagine, I think the left-hand side was the Lunette, which was actually developed. It's a very old algorithm that was developed in 1998, and both of them have been tested on CIFAR 100 dataset, right? So as you can see, Lunette actually doesn't perform very well, but the calibration is very good. And ResNet, on the other hand, gives a very high accuracy, but the calibration is very bad. So this is what we define calibration as. And then the idea is we want to develop models that are not only accurate, but are also well calibrated. So this was the goal that we wanted to look into as part of our, last year's work that we submitted to MICAR. And so we did a little bit of exploration into what causes miscalibration. So what we were able to find is there were many different aspects people had commented on. They said that overfitting causes miscalibration. Large models actually have cause miscalibration depending on the parameters, the batch normalization, and the weight decay. There are several different ways, the reasons why a model could be miscalibrated. And so there are several different techniques that are available for calibrating a model, and the most popular ones actually happen to be this post hoc calibration. What they say is, after the model has been trained, we look at the probabilities that have been given out, and using temperature scaling or Platt scaling, those logits are actually changed to a slightly different distribution to make the network calibrated. Somehow that seems like a slapstick kind of a fix to a major problem, right? We don't want to just take the output probabilities and find a way to change their distribution to make it look calibrated. So the more interesting ones happen to be train time calibrations. The idea is we want to develop a network that inherently is calibrated. We don't want to do some post hoc fix, but we want to be able to make the calibration model, while training itself, it should be calibrated. And so there were some methods that were already published in this particular domain. And what we found interesting was that very simple label smoothing technique, and I'm sure many of you might have come across this, is a very simple regularization technique, but was shown to be a very efficient way of getting a model to be calibrated. And what does label smoothing do? It all just goes away from the idea of this hard labels, right? Instead of saying that when we talk about the class labels, 0, 1, 0, 0, if we have, let's say, 5 or 6 classes, we want to give label 1 to the, the class that it's supposed to be, and 0 to all the others. So label smoothing says, let's not do that, because if by driving our model, even if it gives you, let's say, 0.7 or 0.8, we can still classify it as, belonging to that class. But just because we are trying to match that hard-coded 1, 0, representation, the model keeps on driving towards that particular code. So what label smoothing, was suggested when it's suggested is, it's saying that even by small amount of smoothing, right? So instead of calling it 1, if I go and say it's 0.910, and whatever the difference between 1 minus that 0.910 was equally distributed across all the other classes. So instead of 0, they have now very small classes, right? So this small change had actually shown to be, really good in improving the performance as well as the calibration. And so the label smoothing was basically given this particular equation, where it's showing the cross entropy loss between the hard label and the predicted distribution, as well as this uniform distribution that we talk about after smoothing and the predicted distribution. So this was the suggested solution, or one of the very effective and easy to implement solutions for calibrating a particular model. What we found when we looked into this particular thing was there were some limitations to label smoothing. One was that it was naively trying to do calibration. Like, it was not taking into account what was the current level of calibration, in the particular model at this stage, right? So, for example, if the model is already well calibrated, does label smoothing adversely affect it, or does it cause some of the classes to be even badly, or better? That was not taken into account. The second thing, again, it was that all classes were treated equally. It could very well be that, some classes were well calibrated, but other classes were not. Again, that information was not being taken into account. And majority of the train time calibration methods, although they showed significant improvement in calibration, it was at the cost of some degradation in the performance. So our goal was to try and come up with an alternative, or at least some sort of change to label smoothing technique, such that these limitations were actually addressed. And so the proposed model, which we called it as LS Plus, it was a very simple extension. We didn't do a lot of work on this. All we wanted to say that instead of using this naive uniform prior U, we wanted to replace it with an informed class specific prior. So the two components are informed and class specific prior. So where are those two things coming from? So one is, we said that, of course, this is an additional cost that I have to highlight. This LS Plus actually involves 2 runs of the algorithm. We first train the algorithm using simple label smoothing, and then what we do is we actually feed a validation data set to the label smooth trained algorithm, and then we look at class specific accuracies, right? So for example, if we put the validation data set to a trained algorithm, and we get these accuracies, like for the class wise accuracy, 76%, 79%, 64%, and so on. So those are the class specific accuracies. Now we use these accuracies to design class specific priors for the label smoothing algorithm. So instead of this naive U, we design VK, where we say that VK is now going to have the accuracy itself, if it is that belonging to that class, or 1 minus that accuracy divided by across all the other classes for the remainder. So for example, in this case, if it's a class, this one, we will give 0.64 to that particular class, and whatever is remaining is distributed across the remainder classes. But for class 1, let's say 76% is the accuracy, and whatever is remainder is distributed across the other ones. So these is what we call it as informed class specific priors. The prior is specific to each class, it's different, And we are taking it as informed because we are seeing the current level of the calibration in the model already. We are taking it on the validation data set. And so just by replacing U with BK, our specific prior, we had actually conducted the experiments. Again, three different data sets, Chiom histopathological data, minimalist histo-MHIST, and skin ISIC 2018. Of course, we had several calibration metrics. So calibration has several different metrics, that look at it from a different perspective. So we looked at all of them so that it's not a very biased comparison, and we had compared it with other techniques that actually do calibration improvement, and across two different architectures as well. So we just wanted to make sure that the solution was quite generic and is applicable across different data sets, different architectures, as well as comparatively does better than other calibration improvement techniques. And as you can see from here, we were actually able to show with two different data sets, data 1 and data 2. The third one is not included. And then two different architectures, ResNet 34 and ResNet 15, and the first five are the performance metrics, ACC, AUC, precision recall, and we would like them to be as high as possible. And the last five are the calibration metrics, and so calibration errors, and so we want them to be as low as possible. And as you can imagine, not completely consistently, but our proposed method was able to improve the performance, or at least show on par performance compared to other techniques, as well as reduce the calibration error as much as possible. So this was the quantitative results that we were able to get. The other side that we wanted to kind of explore was the clinical importance of these confidence. How do we interpret them, right? Because we are actually changing based on the LS+ algorithm. So what we would like to have in a clinical setting is that if my sample is getting classified correctly, right, I want it to have a very high confidence. I want to be sure that my model is classifying it correctly. Now, if a sample is getting incorrectly classified, its confidence should be, kind of close to 0.5 or something for a binary task, for a half random kind of a thing. So when we plotted the confidences of these samples for different algorithms, the hard labels, label smoothing, this focal loss and DCA and MDCA, we wanted that kind of a distribution. And as you can see, for most of the algorithms, either they are very highly confident or kind of low confidence. Both the correct and incorrect samples were skewed in the same way. But what we were able to see with LS Plus is when we drew those distributions, the green ones, the correct ones are skewed towards the higher confidence, and the mislabeled ones were actually skewed toward the left, towards the 0.5. And so this kind of gives us a good indication that if the algorithm is able to do this, we can actually have better confidence when we're trying to use the results of the algorithm for a actual diagnosis, or things like that. So that was the main contribution of this particular paper. So hopefully that helps. I think since we're running out of time, just wanted to kind of show some future directions, at least what we as or what I think is the way the domain is headed towards. One of the new things that we are currently exploring is leveraging domain specific knowledge to overcome the limitations in the medical domain, in the sense that it's great to have deep learning algorithms that do everything themselves without a lot of manual intervention and without a lot of this thing. But if we do have some domain specific knowledge, I think it's extremely important to be able to leverage that within the deep learning, so that all the other constraints that we have in the domain are kind of overcome easily, right? Of course, generalizability of the analysis algorithm is again one of the upcoming directions, or at least a very challenging thing, because I mentioned multi-site data, multi-device data, heterogeneous populations, and so on and so forth. So that is again a very crucial thing. I've had several clinicians complain to me about this, that most of the algorithms that you guys develop in labs, when we apply it, they really don't work very well. So generalizability is a very crucial issue. Explainability, if the algorithms that we develop as part of the research labs, if they're supposed to have any kind of clinical, translatability, explainability of this algorithm is, very, very important. Without that, I don't think that next steps will actually happen. And again, from a Indian perspective, one of the things where I see this lacking is benchmark medical imaging data sets. We have a lot of data sets in a lot of different areas coming up, but we see very few coming from the Indian demographics. This is actually very crucial because, as we develop these medical benchmark data sets from our demographics and, have them published, it brings in a large population attempting, these kinds of problems for us as well. So the algorithms that get developed, they can be easily adapted to our demographics, right? So that again is one of the areas that I see as a, in the field where, our contribution can actually go very, very far. So that's all I had, and thanks to my team for contributing to all the research that I have presented to you guys today. If you have any other questions, I can take them.
Thank you so much, ma'am, for an insightful and informative talk. So where participants have at least got the idea that while applying the deep learning algorithms, what are the challenges they will face and how to deal with them. You have shown few of the examples, and calibration is one of the most interesting aspect which you have mentioned. And also for your kind information, participants, this paper was published in MICAI, which is one of the top conference in the field of medical imaging. I mean, the best conference you can say. So participants, if you are having any query, you asked already so many queries, but if you are having, queries, few more queries, you can also ask through the chat box.
How is confidence quantified relative to accuracy, ma'am? If you could give some idea. Confidence. So confidence is the, so most of the deep learning algorithms, for every sample, you actually get a probability. We threshold them to get the classification, the label, right? But before that, we get the probability. So that is what I call it as the confidence. And the accuracy that I'm talking about is not at the individual sample level, because of course it's just binary, right? Whether it was rightly classified or wrongly classified, but it is across the samples. So when we bin them according to the probabilities, for each bin, we say, let's say for example, there are 5 samples in my 0.1 to 0.2 probability bin. In that, I'll see how many of my samples were correctly classified. So that's what we're trying to say, is that that particular curve has to be diagonal. That confidence and accuracy should match up. That's what the idea was behind that. Sure.
गलत फोन कर दिया मैंने आ तो तू भाई कल नहीं तो परसों तो ले आइयो यार.
Yeah, I think there are no more queries, ma'am.
Sure.
Because at least I think everyone has got the idea at least how to apply this two-shot learning and other techniques like knowledge distillation. Those are all, you can say advanced techniques which people are using. So at least we have got some idea, and we will explore more into it, and we'll disturb you in future if we are having any doubts.
Please feel free to contact me if you're interested in any of these algorithms. Would you like to, apply it in your own? I think most of my students do end up putting them on GitHub, but yes, if you do have any queries, please do get in touch with us. Yeah?
So, thank you so much, ma'am, for joining us today and for your nice time. Thank you so much.
Good night, everyone. Bye.
Good night, ma'am. Bye. Yeah, participants.